push record, I'm guessing. Okay, so today we're going to cover the physical properties of organic compounds. So by physical properties, I mean boiling point, melting point, viscosity. That's about how runny it is. So like you can imagine super runny honey, super thick honey, and then molasses. That would be a variant of viscosity on honey. Color then also, like if you think about the honey going from light to darker as it gets more viscous, is also a physical property of organic compounds. And then lastly, solubility, all of which actually you covered in Chem 20. So this might feel like a review, or it also might feel like it's brand new because it's pretty hard stuff, even in Chem 20. Even if you're not in a COVID world, it's still pretty heavy stuff. And so you might find it to be like hardly remember anything from Chem 20. And that's okay. I'll take you through this one step at a time. Okay, and you might still have questions after, and that's fine too. Okay, so the first thing I want to talk to you about is solubility of organic compounds. So if you remember in Chem 20, we use the phrase like dissolves like. And what that means is if something is polar, it'll dissolve in polar things. And if something is non-polar, it'll dissolve in non-polar things. So something that's polar, like ethanoic acid, will dissolve in water because water is also polar. So those two things will be soluble. And something like we covered ethine today. So ethine will not be soluble in water because it's nonpolar, but it'll be soluble in an oil. So the shortcut in Chem 20, and this is out of your notes on page 18. I'm just going to switch my camera so you can see my .chem. The shortcut on page 18 is this, that if it's a hydrocarbon, so alkanes, alkenes, and alkynes are all hydrocarbons because they contain hydrogen and carbon only. Hydrocarbons are non-polar, and therefore they will be soluble in oil and non-soluble in water. Okay, so as soon as you see carbons and hydrogens only, you know it's nonpolar. So for example, remember, let's go to the ones we named today. This is a hydrocarbon, therefore it's going to be nonpolar and it would not be soluble in water. Make sense, everybody? Same with the ethine, would also be non-soluble, not polar in water. Okay. Whereas hydrocarbon derivatives, so all the other things that we covered, so hydrogen, carbon, and something else, so alcohols, carboxylic acids, esters, or if it has a halogen on it, they are polar. So hydrocarbon derivatives are polar, so they will be soluble in water and not soluble in oil. So flipping over to our examples here, this is a hydrocarbon derivative because it's hydrogen, carbon, and something else. Therefore, it'll be polar and it'll be soluble in water. Same with this one, polar, and so therefore it'll be soluble in water, etc., etc. Okay, does that make sense about solubility? Awesome. The last little nugget of solubility is that some are, even though they're soluble in water, some are really soluble in water and some are just kinda soluble in water. So let's have a look at pentanoic acid versus dodecanoic acid. So pentanoic acid is 5 carbons So it'll look like this: 1, 2, 3, 4, 5, double bond OOH. And dodecanoic acid, also a carboxylic acid, but with 12 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Double bond OOH. Okay, so does everybody agree that these are going to be soluble in water? Because they're polar. And I know they're polar because they're hydrocarbon derivatives. So these are both hydrocarbon derivatives, therefore they'll be polar, therefore they'll be soluble in water. Okay, but the question isn't yes or no. The question is which one is more soluble in water, easier to dissolve in water? And the answer to that comes in terms of like percentages almost. So the percentage of this is the polar end here, right? This is what makes this polar. And this is the non-polar end. So in terms of like, do I or do I not want to be soluble? This is about like, let's say 50-50. 50% of it says, yes, I love dissolving in water. And 50% of it says, no, thanks, not really attracted to water at all. Whereas if you look at dodecanoic acid, it's not 50-50. The non-polar end here is like 75%. And only 25% of it is like, yeah, let's dissolve in water. And 75% of it is like, no, hard pass. And so because this has more non-polar than polar, so more non-polar than polar, it won't be very soluble. It'll still be soluble, but just not as soluble. So the answer to the question about which is more soluble in water, pentanoic acid is more soluble in water because percentage-wise, it has less nonpolar end. Okay, any questions about solubility? Awesome. Okay, so now we're going to talk about the physical aspect of viscosity, color, boiling point, melting point, state, oops, at room temperature. I have a feeling there's one more thing that I'm just not thinking of right now. Maybe not. Okay. So I want to show you a little video here. And I also want to remind you of, where'd my notebook go? I also want to remind you of some Chem 20. Oh, guys, I'll have to use this notebook instead today. Okay. All right, so here's a little video I want to share with you. Or maybe not. I don't know where it's gone. Okay, so here I have 1, 2, 3, 4, 5 different oils. These are all hydrocarbons and they're engine oils. And the difference is that in this first beaker, the compound only has, I'm making these numbers up, but let's say 20 carbons long. So it's like C20H42, okay? Then the next one is not going to be C20, but it's like C40H, however many I need there, 84. And then I have C60 and then C80 and then C100, Okay, so as I increase the number of carbons, you can already see the color changing. Light, medium, darker, darker, darkest. So as I get the more carbons in my chain, I have a darker color. As I have more carbons in my chain, it's also going to become less viscous or less runny. Let's have a look. Okay, so they tip them away right away. The first one pours straight out. The second one is a little bit gloopy. The third one is even less runny, even more gloopy. And then the last two are almost like solids. I mean, they want to stick together completely, right? They don't want to be runny at all. And so I want to remind you what it means to pour, what's happening on a molecular level here when we're pouring something. And for that, I want to remind you that in junior high, we talk about a liquid looking like this. Right? These disorganized circles. And if I were to take this box and tip it out and ask these guys to pour, these circles all come tumbling and rolling over top of each other, as if this was like a box of ping pong balls. And some of the top ping pong balls are going to come forward, and then maybe the second layer, and then maybe one from the back layer, and they all kind of topple over top of each other when they're pouring out into the other beaker. So this is what this means. Hold on a minute. Boom, 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 boom. So these are all toppling out of each other, one ball over top of each other. If I zoom in to what's inside these circles, it really is these 20 carbons all bonded together. So I'm not gonna draw the carbons. That was a bit of a bad start there. Let's do it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20, right? In a circle. And then 20 in a circle, and then 20 in a circle, etc. And so these are those circles here. 3, 4, 5, 1, 2, 3, 4, 5, all trying to topple over each other to pour out of the beaker. So what's holding these close together are these intermolecular forces. Intermolecular forces. The intermolecular forces, or in other words, like the attraction between this molecule and this molecule, is what's keeping them close together. If you imagine that these were each a bar magnet and the bar magnets were super strong, they're not going to tumble over top of each other. In fact, they're going to stick together like a solid. They're going to be like that last beaker. When they come out, it's going to be a conk, not a tumble over top of each other. Whereas if they have, let's say, no magnetic field at all, then they're just going to fall out of the beaker, no problem. They're just going to tumble over top of each other, no problem. And that'd be like the first beaker. So the stronger the intermolecular forces, the more viscous, the darker, and the higher the boiling point, melting point, more solid-like. That's the same. I'm saying the same thing 3 different ways there when I say that. Okay, so intermolecular forces play a big part in viscosity, color, and boiling point, melting point, if it's a solid, liquid, or gas, or room temperature. So a reminder now about you went and named chloromethane as our warm-up. It looks like this, right? You went and named that as chloromethane. So these circles here look like this for chloromethane. Oops. And the intermolecular forces are the forces that are in between these two molecules. They are not, I repeat one more, not those sticks. Those sticks are called as in an intramural would be within the school, intramolecular forces. And most specifically here, they're called covalent bonds. And other kinds of intramolecular forces are ionic bonds and metallic bonds for metals. I am not breaking these when I boil something. Like when I'm melting ice, it's still H2O. I do not break the H's away from the O's. So same thing here. When I am boiling this, I'm not going to break this. As soon as you talk about breaking covalent bonds or the carbon and hydrogen separating from each other, you go straight from mastery level to 0 level. That's a killer. As soon as you start talking about intramolecular forces here, these circles stay together. They just tumble over top of each other, or they simply move, right? If this was now going to become a liquid, a gas, like I'm boiling into a gas, I just have these circles farther apart, but I haven't destroyed the circle. It's still the same. What are the forces of 20? Just further apart from each other. I've just weakened the forces in between them, right? I've just taken these two magnets and I've moved them apart from each other, so there's less attractiveness between them, right? So intermolecular forces here and intermolecular forces here. Okay, so when I'm boiling my chloromethane, I'm simply just taking these circles and I'm moving them further apart from each other, moving these intermolecular forces away from each other. And as in an international event, so between two different nations, between two different molecules. And these are called forces because they're not like bonds. They really are. They just get weaker and weaker as you get further apart, like gravity. Gravity is still there. Even if you're an astronaut floating in space, it's just less and less there. Okay, whereas a bond is kind of a yes or no. A force is a weaker, stronger. Okay, and there are 3 types of intermolecular forces: London dispersion forces, which are in all molecules; dipole-dipole forces, which are only in polar molecules, which is great. We just covered polar when we talked about solubility, right? So we can already identify if it's polar or not polar. This is a hydrocarbon derivative, therefore it's polar, therefore it'll have dipole-dipole. And the last type is hydrogen bond, which is like a dipole-dipole on steroids. Okay, so if it doesn't already have dipole-dipole, it's definitely not going to have a hydrogen bond. And the 3 types of things that have hydrogen bonds are HFs. And it's not this because that's a covalent bond. That's over there in the red. This and this, it would be their bond in between each other here. That's the hydrogen bond. So this circle and that circle, this molecule and that molecule beside each other. The analogy I use is like a grilled cheese sandwich. These 2 things are the bread, right? And then the hydrogen bond is like one type of cheese that's holding these 2 breads together. And of course, if I move the breads apart, the cheese just gets stringier and weaker. Some of the cheese breaks, but mostly just gets weaker. But I'm definitely not breaking bread here. The other types of hydrogen bonds are NH and OH. And then a new one in chemistry is the carbonyl group, the COOH, to water, by the way. That's only to water. Well, it's only to an OH. I'll put that actually, because it's only to an OH, not necessarily water. We put that in purple. Okay, so this HF to HF, that's that molecule finished. There's only one stick allowed on hydrogen, one stick allowed on fluorine. And so that's that molecule finished. If this was a fluorine here and a fluorine here, it does not have hydrogen bonds because this isn't an HF bond. This is a HC bond. You can kind of see it obviously here, but if I wrote it like this, it looks like it might have an HF bond, but it doesn't. The only thing that has an HF bond is actually HF, because then it's done. Okay, whereas these guys, there's lots of combinations that you can have an NH bond because nitrogen can have 3 sticks on it. And so I could have 2 other things attached to that nitrogen that's beyond the hydrogen. Okay, so this, and then this specific situation of a carbonyl group with the OH group can form a hydrogen bond. Okay, so we got all of them, only polar ones, and polar ones on steroids. Okay, that, by the way, is all on page 18 of your notes as well. Any questions before we dive into some examples? Okay, so let's go back to the ones you named as part of your warm-up. And let's list their intermolecular forces. So there are 3 types: London dispersion, dipole-dipole, and hydrogen bonding. First of all, we know that all molecules have London dispersion forces. So right away, I can put London dispersion force, London dispersion force, London dispersion force. Awesome. Then who has dipole-dipole? Well, polar molecules have dipole-dipole. So this is a hydrocarbon derivative, therefore it's polar, therefore it'll have dipole-dipole. This one is a hydrocarbon derivative, therefore it's polar, therefore it'll have dipole-dipole. This we already decided is nonpolar because it's only hydrogens and carbons, and therefore it doesn't have dipole-dipole. This one will have dipole-dipole, this one will not, and this one will have dipole-dipole. Okay. In terms of hydrogen bonding, this doesn't have an off, nitrogen, oxygen, fluorine, nor does it have the carbonyl group with an OH. This, though, does. First of all, it has an OH and it has a carbonyl group with an OH. So this has lots of hydrogen bonding. In fact, I'm going to put ×2. This does not, it doesn't have any dipole-dipoles. It's definitely not going to have hydrogen bond. This has an OH, therefore it has hydrogen bonding. This does not. And although this has a carbonyl group, it doesn't have the OH. So it can't hydrogen bond with each other. It could hydrogen bond with water, but I want to talk about its boiling point. So that'd be with each other. Solubility would be with water. Okay, so that's like an overview of what intermolecular forces are and how to apply them to a specific molecule. And now I want you to talk about predicting boiling point. So how do we take these molecules and put them in order of boiling point? The first thing I would do is I would do exactly what I've just done. I would take the molecule and list the intermolecular forces, take the molecule and list the intermolecular forces. So I've already done number 1, listing the intermolecular forces. And then the more, I've already written this down on my notebook, the more intermolecular forces, the higher the boiling point, and the more viscous, and the darker, and etc. Okay, so the higher the boiling point. So I can already kind of rank them. This one is going to have the highest boiling point because it has 2 hydrogen bonds, dipole-dipole and London dispersion forces. So in terms of lowest to highest, the highest is going to be my C2H5COOH. It'll be the highest. And my second highest is methanol here. So I have CH3OH is my second highest. So those are those 2 talked about. I have somebody knocking on the door. Hold on 1 second. Carter, Presley's here. Can you play outside? No. Okay. He's still in class. Can you come up on your door when he's done? Okay, he'll do that. Okay, thanks, Presley. Home teaching and home parenting at its finest. Sorry. Okay, so there's those 2. Those 2 are taken care of. Oh, those 2 are taken care of. And then I have these 2 are tied and these 2 are tied. So those are done. And then I have a tiebreaker between, hold on a minute, I'm having a hard time kind of communicating what I want to communicate to you, but that's okay. Okay, so these guys are done. Then now these guys are tied because they have two intermolecular forces each. So these guys are finished because this has 1, 2, 3, 4 essentially. This has 1, 2, 3. So that's how I organize these guys. And then I have, these are tied for 2 intermolecular forces each. So who's going to be higher? So if there's a tie, we talk about number of electrons. So you could count the number of electrons in here and count the number of electrons in here, but that's really hard for us because, like, just thinking about chlorine, we would say to ourselves, oh, there's 7 electrons. No, there's not. There's 7 valence electrons, but actually there's 8 underneath that and then 2 underneath that in our Bohr diagram. Oh, that's right. There are 17 electrons. That's, it's not natural for us to do that anymore. We can do it if I force you to, but it's not very natural. So the shortcut, but never ever write this down. The shortcut is the molar mass. The more electrons, and we're going to do molar mass, but never write that down. Okay, always write down electrons because that's the real thing. But we're going to calculate molar mass because that's faster. So the more electrons, or the more molar mass, the more London dispersion forces there are. And therefore, the higher the boiling point in that tiebreaker. Okay, so out of these two, which is going to have the higher molar mass? Well, the one with 3 carbons and 2 oxygens. So this has a higher molar mass, more electrons, higher boiling point. And so I'm going to write down that I have my CH3COOCH3 next, and then my CH3Cl will go underneath that. So these had 3 IMFs, these had 2 IMFs, and I figured out the tiebreaker because of the molar mass, number of electrons, and then 1 IMF. Now I'm down to these two, 1 IMF and 1 IMF. So 1 IMF, and I have a tie again. I'm gonna go to the tiebreaker, which is about electrons. This one will have the higher molar mass, more electrons. So therefore it'll have a higher boiling point. And so this one is going to then be C2H2 and CH4. So lowest, second, third, fourth, fifth, and highest boiling point there. Okay, any questions? Kind of messy, hey? Okay, we can do, I definitely want to do this last example, but do you want to see this middle example before I move on to the last example? Like, do you guys want to see 2 examples or 3 examples? Give me an emoji if you want to see both examples done today. 2 more examples done today. Okay, and now give me an emoji if you want to just see 1 example done today, 1 more. Just 1 more example. You got to vote. Okay, just 1 more example. Okay, so I'm going to skip through this one. We're going to go to this one. Uh-oh. Oh, I see what I need to do. Okay, so here are 1, 2, 3, 4 molecules. This is actually stolen from an old diploma question. There are 4 molecules here, and it wants them in order from highest boiling point to lowest boiling point. Let's number them, or let's letter them. A, B, C, D, and then I'm going to put them from highest to lowest in terms of B, C, A, D, or whatever it ends up being. So first of all, they're isoelectronic, which is my way of teaching you another vocabulary word. Iso meaning same, electronic meaning electrons, so the same number of electrons, or their molar masses are the same. And so that's not, so our second tiebreaker isn't going to work. So we're going to need a third tiebreaker. Okay, but the first thing that we're supposed to do is we're supposed to list the intermolecular forces, right? That's the first thing that we do in order to rank their boiling points or predict their boiling points. And so this listing the intermolecular forces, they're all going to have London dispersion forces. I notice this is a hydrocarbon derivative, and so therefore it's going to be polar, therefore it's going to have dipole-dipole, but no hydrogen bonding. This is nonpolar because it's only hydrogens and carbons. This is polar, so it's dipole-dipole, and it has an OH, therefore it must have hydrogen bonding. And same with this one, dipole-dipole and hydrogen bonding. So in terms of highest to lowest, so far, these guys are tied for my highest because they have 3. This one is definitely my lowest because it has only London dispersion forces, 1 intermolecular force, therefore it'll have the lowest boiling point. This has 2 intermolecular forces, London dispersion forces and dipole-dipole. 2 intermolecular forces is going to be a slightly higher boiling point, but now these have 3 intermolecular forces. So is it going to be CD or DC? Okay. And then A and then B. So that was the first thing that we're supposed to do. The second thing that we're supposed to do, or the first tiebreaker, is number of electrons. But it says that they're isoelectric. They're going to have the same molar mass. They're going to have the same number of electrons. These guys are isomers of each other, right? Same number of carbons, hydrogens, and oxygens, just different structures. So they're isomers of each other. So I can't use that as the tiebreaker because they're still tied. So they have 3, and then they have the same number of London dispersion forces. And so the third tiebreaker is shape. So we talked about how the more intermolecular forces, the higher, the more electrons, the higher. And so now the third tiebreaker is about shape. And what we talk about shape is the flatter, the higher the boiling point. Now that has to do with surface area. So if I have a look at the shape of these molecules, this is circular in its shape. And so I'm trying to take 2 circles, like 2 basketballs, and I have the intermolecular forces in between them, holding them together. And these are oval shaped. And so here I have 2 oval molecules, and the intermolecular forces are in between them that I'm trying to pull apart. Well, let's just talk about, like, if these were basketballs and I were to pour a bunch of glue, intermolecular forces, in between these 2 basketballs, let that glue dry, and then pull those basketballs apart. That'd be pretty easy to pull those basketballs apart because the glue doesn't have enough surface area in which to stick those basketballs. Whereas these guys are like planks of wood. If I were to pour the glue in between the 2 planks of wood and then try to pull them apart, it'd be much harder, even if it's the same amount of glue. So because I have a flatter shape, then I have more surface area for it to interact with, and therefore it'll have a higher boiling point. And so the highest boiling point is going to belong to D, and then C is next, because not only D has 3 intermolecular forces, but it's also flatter in its shape, whereas this has 3 intermolecular forces. And the word that you use instead of flatter is bulky. And so the order is going to be D, C, A, B in its you know, when we're done. D, C, A, B. Okay. So, and then also, like, in terms of colors, darkest to lightest. In terms of viscosity, thickest to thinnest. Okay. And in terms of solubility, soluble, not soluble, soluble, soluble in water. Okay. That's it. It takes practice now. That's right. It just takes some practice to go through them all and navigate, like going through all those steps yourself and remembering to do all three things by yourself. But that's the whole full meal deal. Okay, any questions for me about what we just covered? Okay, you can hang out for a little longer if you want to ask some one-on-one questions. Otherwise, tomorrow. So tomorrow